Welcome to Ask and Learn.
We want to sketch the curve y is equal to x times x minus 4 cubed. Now in this chapter, they give us a laundry list of steps we should follow in order to graph something. So let's just go ahead and follow them step by step. So the first thing they suggest that we do is to determine our domain. So we have a polynomial here, a factored polynomial. And we know that the domain of a polynomial is just all real numbers, or negative infinity to infinity. The next thing they say we should find is our intercepts. So our y-intercept is going to be when x is equal to 0. So we're going to have y is equal to 0, 0 minus 4 cubed, and that's just 0. Our x-intercepts are going to be when y is equal to 0. So we're going to have 0 is equal to, actually let me go ahead and write this up here. 0 is equal to x times x minus 4 cubed, and we can use the zero product property to get that x is equal to 0 and x is equal to 4. The next thing they suggest we do is to look for symmetry. Now, we know that this is not going to be a periodic function, but we can check to see if f of negative x is f of x or negative f of x. So plugging in that negative there, we get negative x minus 4 cubed. Now we can factor that negative x out and it would become negative 1 cubed. So negative 1 cubed is just negative 1, and the negative out front cancels, so we get x plus 4 cubed. Now this does not equal to f of x, nor is it negative f of x. So what this tells us is we have no symmetry. The next thing is we want to look for asymptotes. Well, we know this shouldn't have any asymptotes due to it being a polynomial, but we can use that same logic to look at the end behavior. So let's just go ahead and do that. So the limit as x approaches infinity of f of x, well, in this case I mean f of x being our function over here. Well, this is essentially y to the 4th power, just because that would be the largest degree, and the coefficient would be just 1. So we know that even degree polynomials with positive coefficients go to infinity, and we know that the end behavior on both sides of even degree polynomials will be the same. So we get that our end behavior will be infinity and infinity. Now the next two steps, I'm going to go ahead and merge into one, and it's finding our intervals of where the function is increasing or decreasing, and also we want to look for max/mins. So let's just go ahead and do this on another page to save some space. So we have y is equal to x times x minus 4 cubed. So we have two functions being multiplied together, so we're going to need to apply the product rule. So remember, product rule says first function, take the derivative of the second, and multiply them together over cube. And then we're going to add them in the opposite order here. All right, so first we know the derivative of x is just going to be 1, so let's just go ahead and simplify that. And then to take the derivative of x minus 4 cubed, we're going to have to apply chain rule. So chain rule says take the derivative of our outside function, which in this case is going to be x cubed. So that would be power rule, so 3x minus 4 squared, and then we need to take the derivative of our inside function, which is x minus 4. Now the derivative of x minus 4 is going to be 1 because derivative of x is 1, derivative of 4 is 0. Oh, not 0, 1. And then here we just have x minus 4 cubed. All right, now let's go ahead and factor out x minus 4 squared. And doing that will leave us with 3x plus x minus 4. So on the inside here, we get 4x minus 4. So we can factor a 4 out as well. So 4x minus 4 squared, and then x minus 1. All right, so we have y prime. And if we were to set this equal to 0, we would get that our critical points are going to be x is equal to 1 and x is equal to 4. So we'll need these critical points in a minute. We can look at these to see if these will be max or mins. All right, so we now know that y prime is equal to 4 times x minus 4 squared and x minus 1. All right. And what we want to do to figure out where it's increasing or decreasing is figure out where y prime is strictly larger than 0 and strictly less than 0. So for increasing, we want y prime to be strictly greater than 0. And just to save us some time, I went ahead and did this earlier, because otherwise it would make the video a little bit too long. So this function is increasing on 1 to 4, and then 4 to infinity. And we can figure out where this function is decreasing by looking at where y prime is strictly less than 0, and then once again, just for the brevity of the video, I went ahead and did this already. It would be negative infinity to 1. So let's go ahead and put those critical points we found before down here. So we had that x is equal to 1 and x is equal to 4. So now we're going to apply the first derivative test. All right, so to the left of x is equal to 1, we know the function will be decreasing into x is equal to 1. And then after x is equal to 1, we know the function is increasing. So it decreases into 1, increases after. So we know this should be a local min. So I'm saying max and min, but I should be saying local max and mins. And now x is equal to 4, so it's increasing into 4, and then after 4, it's also increasing. So this is not a max or a min, it would be a saddle point. All right, so we have our max and our mins tackled. The next thing we want to do is check for concavity and inflection points. So concavity / inflection points. So that means we want to look at y double prime, and let's just go ahead and go back to that last page and figure out what y double prime should be. So y double prime is going to equal to, well, the derivative of two functions being multiplied together again. And remember, since 4 is a constant, we can just go ahead and factor that out since the derivative is linear. Minus 4 squared and x minus 1. All right, so we're going to apply product rule once again. So we're going to have x minus 4 squared times the derivative of x minus 1 plus x minus 1 times the derivative with respect to x of x minus 4 squared. All right, so we get x minus 4 squared. So just like before, the derivative of x minus 1 is just going to be 1. And if you take the derivative of x minus 4 squared, we're going to have to apply chain rule again. Chain rule. So first we use power rule. So it would be 2 x minus 4 now to the first power. And then we need to take the derivative of our inside function, which is x minus 4. And again, the derivative of x minus 4 is just going to be 1. 4. So let's go ahead and clean this up a little bit. So first, let's go ahead and factor out x minus 4 from this. So we get x minus 4. So that would leave behind x minus 4 there, and then plus 2x minus 2. So 4x minus 4. Simplifying the inside here, we would end up with 3x minus 6. And we can factor a 3 out of there to get 4 times x minus 4. Forgot I factored out that 3, so it should be 12 out front here. Then x minus 4 and x minus 2. So if we set this equal to 0, we would get that our points x is equal to 2 and x is equal to 4. So we can use these in a moment to look for points of inflection. All right. So let's go ahead over here and write down what our second derivative is, which should be 12 times x minus 4 times x minus 2. And to figure out where to concave up and concave down, we're going to need to look at where y double prime is strictly larger than 0 and strictly less than 0. So concave up is when y double prime is strictly larger than 0. And then once again, just for the brevity of the problem, I went ahead and solved this already. So this is going to be negative infinity to 2 union with 4 to infinity. And over here for down, this will be when y double prime is strictly less than 0. And we would be from 2 to 4. Now, our two possible points of inflection are going to be x is equal to 2 and x is equal to 4. So now let's go ahead and see. So to the left of x is equal to 2, we are going to be concave down. To the right of 2, we're going to be, to the left of 2, we are actually on this interval here. So we should be concave up. And then to the right of 2, we're on the other interval for being down. All right, so this here would tell us we have an inflection point because concavity changes at x is equal to 2. And then at x is equal to 4, after 4, it will be concave up. So both of these are points of inflection. All right, so that was everything they suggested we do before we actually start to sketch this. All right, so let's go ahead and first just plot down our intercepts. So we have our y-intercept would be 0, 0. Our x-intercept should be 0 and x is equal to 4. So 1, 2, 3, 4. So there was no symmetry in the problem. Our asymptotes, well, no asymptotes, but we at least know the end behavior of this graph is going to be going to infinity on each side. we know we are going to have a local min at x is equal to 1. So there's a min around here somewhere, and we could figure out whether that needs to be above the x-axis or below the x-axis in a second. And at x is equal to 2, so maybe actually above the 1, I'll put min, and then at 2 and 4, we will have inflection points. So I, P, I, P. All right, so let's go ahead and start with this. So we're going to start from infinity, and we're going to go down until we hit our first critical point, which is going to be 0, 0. And then at this point, our next important point is our minimum at x is equal to 1, so we know it's going to curve up something like this here. And at x is equal to 2, we're going to have a change in inflection, so it starts to go from concave up to concave down. And at x is equal to 4, we'll have the same thing. So it kind of slowly comes in and then does something like that there. So maybe that curve at x is equal to 4 should be a little bit more intense, something kind of like this. So it should kind of flatten out a little bit more. But we've used everything over here. We've used our inflection points. We can see the concavity where it's increasing and decreasing. And if I was able to draw a little bit better, that might look a little bit prettier. Something else you could do is go in and maybe say what value this occurs at. But as far as I'm concerned, since we are just trying to, as well as this inflection point there, but as far as I'm concerned, just because we're trying to sketch it, I don't really think these numbers matter all that much.